Let's calculate the potential at a point P where we have a finite rod of a charge density lambda, uniform, and I'm going to place a point P here at the end. And remember, out here, this is infinity, and I'm choosing my 0 to be at infinity. And I want to calculate v of p minus v of infinity, which is 0, using our formula for the potential, the superposition principle, where we do k dqs over the distance rs to the point P, integrated over this short rod. Now, once again, the key to all of these calculations is to choose a coordinate system. And I can choose a coordinate system a variety of different ways. I could pick my origin at the center of the rod. I could put my origin here at the end. I'm just going to choose my origin out here. I'm going to call this x equals 0 at the end. And now I want to try to show you another way that we've written this, just so that you can see it. I'm going to pick a little element dqs right there. And we wrote this as k dqs, a field point vector, minus a source vector that was our integration vector. And let's just draw those out so you can see what they are. So this is a vector from the origin to the field point. I had to displace it a little. And this is the vector from the origin r, s. And now I can continue my coordinate system if I choose this to be my positive y-axis. Now remember, we're only taking magnitudes, so we'll use vectors, but we'll take magnitudes at the end. I write my field vector as the position x of the field point I hat, where this distance is xp, going from the origin to there. So here we are at xp. And here's the key thing. My integration variable, I'm going to write as x prime I hat, where this distance is x prime. And so rp minus rs prime is just the magnitude. Now what we have is simply xp minus x prime. And so that's how I've expressed the denominator. Now the dqs, this again, remember, x prime is the integration variable. And so I need to express, just like we did with Coulomb's law, the small charge here in terms of the integration variable. And what I can do is I can call this distance dx prime, and then the amount of charge that's on this small element is the charge density lambda times dx prime. Now, often, sometimes people will write this as lambda dl. And that's true abstractly, but it isn't relating to our integration variable. So we don't want to do that. We want to write our dq in terms of the integration variable. And now you can see why. Because that the potential at the field point minus our 0 at infinity is the integral over this rod. And what are we integrating our integration variable from? Well, we're just taking little pieces. And by the way, that's why we choose dqs at some arbitrary point. We don't choose it at the origin, because then x prime would be 0, and we couldn't set this up. And we're integrating x prime, our integration variable, from 0 out to the end of the rod. And let's say the rod is length L. So we integrate out to L. And now we can use our results. We have lambda dx prime over xp minus x prime. And here's an integral that's very straightforward to do. It's equal to minus k lambda, the natural log of xp minus x prime, evaluated from x prime equals 0 to x prime equals L. And when we put those two pieces in, we have the natural log of xp minus L over xp. And if I want to flip this, I get k lambda of xp over xp minus L. And this potential difference, depending, we've missed a lambda here, have to be careful. So let's get our lambda outside. And this quantity will be positive or negative depending on the sign of lambda. For lambda positive, we see that this quantity is greater than 1, so the log is positive. So the potential at our field point, xp, is positive. So for this positive charge, that's a positive point. And when lambda is less than 0, the potential there will be negative. And now that we have our potential function, we can use, if we wanted to move charges anywhere in the presence of this rod along the x-axis, we can use conservation of energy. And you should try that problem out yourself.